talk, and I did tell Indranil that it is characteristic he talk. In fact, he has attended the same talk, and still he agreed, and he still wanted me to talk. So you should blame him. But I would try to introduce some complex number in the end. So, yeah. But is it audio? Yeah. Okay, so generally I would prefer to work in a Neutron local ring. Just for the audience sake, I will change my track a little bit. So I'll think of this pair XOX1. So by this pair, I mean X is a projective variety. Over K, let's assume K is algebraically closed. And characteristic of K is P positive. And OX1 is a fixed polarization. So given this pair X and it's with a polarization, we know we can associate a degree, concept for degree. So I'll quickly recall, I suppose everyone is familiar, but I'll just say it. Consider this number, Euler characteristic, which is alternating sum of the cohomology of the n twist. Okay, so this we know is a polynomial. In fact, it would look like E0 n plus d minus 1, choose d minus 1, where d is dimension of the variety, minus E1 n plus d minus 2, d minus 2, and so on. Okay. So this is a polynomial. Now, given this pair, suppose I think the corresponding homogeneous coordinate ring, which is many people call it section ring. So H naught OX M, n greater than or equal to 0. So this makes it a graded ring, Rm. Nevertheless, for my purpose, I can assume it is standard graded ring because first few components do not matter. So this one just says, if I look at length of R mod I to the power n, so what is I? I, for example, you can think as an irrelevant maximal ideal, but in practice, the way to think of I is some ideal I in R says that length of R mod I is finite. So if I look at this ring, so it is just the length of R0, so minus 1. So why am I writing this? So this is, this just says that this is again, this is for n large enough. So this will look like n plus d, choose d, minus E1, n plus d minus 1, choose d minus 1, and so on. Okay, so this is, we know this pair E0, which is associated with the ring Ri, or associated with the pair X and OX1. So this is an integer. This is Hilbert-Samuel polynomial, and this is an integer. It's called a degree of X, and in practice it's called multiplicity. Actually, I'm doing fine. For the pair Ri. So this, I'm not sure, so I guess people are quite familiar with this notation. So this, another way of looking at this would have been I look at E0 of this pair as a limit of length of R mod I to the power n into d factorial upon n to the power d. Okay. So I can do the carry on the same thing for any pair Ri, R local. I think this notion is useful for singularity purpose now. And length of R mod I is finite. I can make the same assertion. So this happens. So this is pretty well studied. I mean, this is a positive integer, in particular greater than or equal to 1, and it fits very well in cohomological way. So the some properties I would recall that E0 is invariant under hyperplane section, a general hyperplane section. So be that in a projective variety or in a local ring. Second, E0, in fact, Hilbert-Kunz function itself is invariant in a flat family. Okay. So given a pair or a XOX1 or the Ri, I have this integer called multiplicity of the pair. Now suppose your ring characteristic of K or characteristic of the ring, I should say, is positive, then I can similarly define another function. So this is called HK Hilbert-Kunz, I'll give a name, Hilbert-Kunz function. So this is defined as follows. You look at the nth level, so it's a function, HK is a function from include 0 also, so it is a length of R mod take nth Frobenius of R. So what is nth Frobenius here? It will be something like, suppose if I take a map from R to R, x goes to x to the power Pn. So nth Frobenius of the ideal will be something, you take x1 to the power Pn, xs to the power Pn, where xi's belong to, xi is a generator of I. So take the generator, lift them to the power P to the power n, and that's your Frobenius. Is that okay? So maybe I'll write it here. This is equal to length of R mod I to the power square bracket In, where I P2 is x to the power Pn, where x belongs to I. Take the ideal generator. So you can just take generators of, this will be generated by generator, Pn the power of the generators of I. So, okay, you have this. So you have a Hilbert-Kunz function. So it makes sense to talk of this number HRI, which I define as limit of n tends to infinity. So now alternatively Pn will be denoted by Q when there is no confusion. So EHK I can define as length of R mod I to the power Pn, just imitating our Hilbert-Kunz function, and P and D, where D is dimension of the ring. So first of all, you should ask whether this limit exists. So this was a result of Monsky. In fact, you can write this HK function of the pair of Rin to be EHK Ri Q to the power D plus big order Q to the power T minus 1. So here it is no more I can claim that this E0, I mean this length of this thing behaves like a polynomial. that is actually not true. This is not, but the thing you can assure is this, ensure is this. And what do you mean by O of q to the power d minus 1? So I mean, if I say Fn is of order g of n, I mean there exists some positive constant such that f of n is less than or equal to c of gn. So he proved this, and so now from the very definition of the multiplicity and the EHK multiplicity, it's obvious that there is some relation between them is as follows. EHK of Ri is less than E of Ri. So what he ensured, he said, is a positive rational number, positive real number. So this was a question now. So in dimension 1, he proved that this function I can write, in fact, as now, from this we call this clear dimension 1, this coincides with your use of multiplicity. So it is E of Ri into Q plus delta n, where delta n is a periodic function. It's a genuine periodic function, in fact, for n large. So for the dimension 1 itself, this doesn't behave like a polynomial. So here it is. Now, what about dimension r greater than or equal to 2? So the question was, is this a rational number? At least EHK. So this computing this turns out to be a difficult task. So he introduced this function in, say, around early 80s. This one, and several people have computed various examples. So till date, I mean, just you take a hypersurface, for example, a polynomial ring, and ask what is this EHK? You do not have definite answer. So they have proved for certain kind of hypersurfaces, or using like a monomial rings or that kind of thing, using various techniques. Okay, so I won't go into that now. The thing, why the question then one should ask, why is it difficult? Why is it so difficult? Because E naught was easier to keep, because you just keep cutting the dimension and you come to the 0 dimension, count the points. So why is happening? So in that light, we should see 2 examples of Monsky. So they tell you already the obstruction. So take a plane curve. So it's given by degree 4 equation. And let characteristic of K be P. Okay. So this, he said EHK of R. So when I say EHK of R, means with respect to maximality here, I mean. So this is equal to 3 plus 1 upon P square. If P is congruent to plus or minus 3 mod 8, if P is congruent to plus or minus 1 mod 8. His answer is 3. This is example 1. So this example tells you immediately that your induction method is not going to work, because in this, there's a 2-dimensional ring for your purpose, and when you go modular dimension, it becomes go cut down by a general hyperplane, it becomes a dimension 1. But in the dimension 1, EHK coincides with your usual multiplicity, which is not dependent on the underlying characteristic. And so an induction is not going to work. It is not invariant under general hyperplane section. Okay, then the other example he wrote is A1K. So A1K is a polynomial in one variable. So this I'm looking at the curves parameterized by A1. So this is let R lambda be K X fiber over the fiber over lambda. So Z4 minus xy, x plus y, x plus lambda y, where lambda belongs to A1 minus 0. Okay, so here characteristic of K is fixed, it is 3. So he said EHK of R lambda is 3 plus 1 upon 3 2D lambda. So I'm defining D lambda, where D lambda is algebraic degree lambda over Z naught 3Z. And if it is transcendental, then you define to be infinity. So this suggests that your EHK is not an upper semi-continuous function. And so in particular, it doesn't stay invariant under flat deformation. So then the question we ask then why we should be interested in EHK. So the question, so EHK is, the answer is EHK is more powerful invariant compared to your usual multiplicity. So few of the things I will recall is especially characteristic P kind of singularities. So one is if I take R to be a domain, strictly speaking, I should say analytically unramified. So take a complete domain, for example, complete powers, quotient of a complete power series ring. Then EHK of R is 1 if and only if R is non-singular. So that in that particular way it behaves exactly like your usual multiplicity. Okay, but the philosophy is actually now that of course EHK is always greater than or equal to 1, but not so. I'm sorry, that's not correct. General philosophy is that smaller the EHK, better your singular characteristic P singularity is going to be. So how's that? So let us recall another thing. So suppose EHK of you take a ring is less than 1 plus 1 upon D factorial, where D is a dimension. D is the crude dimension of the ring. So this implies that R is F regular. So I won't say much about this one. This is so F regular is it's something which is which involves tight closure of things. So like so it says all ideals are tightly closed. So whatever that means, the use of this is first of all checking something is F regular is a very intrinsic method of checking it because it depends on the ideal. So do not go to any resolution to check for it. Okay. And other things, suppose I start with a ring which is in characteristic 0 or variety and go mod reduction P. If for infinitely many P it is F regular, then your ring is going to have a rational singularity. So it checks automatically. So, okay. And third thing, this is actually a conjecture, it's still standing conjecture, not completely solved. Suppose I denote my R PD to be a quadric hyperplane, so quadric plane, so quadric hypersurface, x naught b modulo x naught square plus x1 square plus xp square, where characteristic of your field is p is not 2, should be greater than 3. So this is your ring. People think that you don't need the hypothesis fp bar, you can take any algebraic closed field of characteristic p. The assertion is this. I'll define this notion. It's a unmixed ring of dimension D and characteristic P. So unmixed is geometric concept. So it's saying it doesn't have any embedded lower dimensional component. That's all it says. Because lower dimensional components do not show up in the computation of EHK. So suppose you have this ring. So EHK of n, if Rn is not regular, it's not smooth or regular. So if it is regular, then its EHK is going to be 1, of course. So that's not the thing. But it's not regular, then it's always greater than RPD. So the quadratic hypersurface is the lowest EHK multiplicity it takes in the class of singular rings. That's one part. The striking thing I find it is that it says if the equality holds in this, then your ring is this ring R is analytically isomorphic to that ring. If residue field is same, so residue field of then it just says R is isomorphic to your RPD. So this is the conjecture of Watanabe and Yoshida. So they had proved up to, so let me write their name. So they have proved up to dimension less than or equal to 4, then other people came and they proved for dimension less than or equal to 6 now, so it is valid up to that. Okay, so now this is, then other thing, one more thing I would like to mention is follow. Now this, you take a projective non-singular curve. So it's going to be a proj of some ring R, where R is two-dimensional. I assume it's two standard graded ring. Okay. And V be a vector bundle. Okay. So you have a curve, you have a vector bundle, and now you associate set of numbers to V, which I call strong Hn data related to V. So I'll define it in a moment. AIs, bunch of RIs, and D. So here D is a degree of X. What you do? So there exists some S large enough such that V, if I take sufficiently large progress pullback of V, it will have a Hn filtration of this type, VL, V0, V1. Where V upon Vi minus 1 is a strongly semi-stable. And mu of Vi is greater than mu of Vi Vi plus 1. So this is a theorem of Langer. It's the first sufficiently large enough propionese pullback will achieve a strong Hn filtration. This is a problem. This problem occurs very peculiar to characteristic P because in characteristics 0, all semi-stable bundles are strongly semi-stable. So once you have Hn filtration from V, for any finite map you pull it up, it's going to remain Hn filtration. But characteristic P it doesn't. That is the problem. So nevertheless, you'll achieve some number S where this will happen. To go to that state now, so let number AI of V be mu of Vi upon Vi minus 1 and normalize it by PS, and Ri of V as rank of Vi upon Vi minus 1. So since I have normalized, this data is unique now. So far what we have done is you have a vector bundle on a curve and you associate a set of numbers which I call a strong bundle. Is this up to this point? It's okay. Or should I? So okay. So just now I said up to dimension 1 that case was clear. So this is a case of dimension 2 graded ring. So you look at this situation, 0, you consider this particular vector bundle, which is a Suzuki bundle given by OX1. In fact, I could do with any ideal of the ring, graded ideal, but just for simplicity, I consider this. So given given OX1, you consider Suzuki bundle, then this was a theorem of Brenner and myself independently. It just says that your EHK of this ring will be given by these numbers, E mod 2, where it is the degree of the curve, summation Ri Ai square upon 2D. Okay. So in particular, EHK is a rational number for two-dimensional graded itself. Okay. Not only that, you also proved that EHK of R is always greater than or equal to this number, D mod 2 into R plus 1 upon 2. R is rank of the vector bundle. And then only this, it says suppose EHK of R is equal to D mod 2 R plus 1 upon 2. If and only if B is strongly semi-stable. So EHK, you look at the EHK decides whether bundle is strongly semi-stable or not. Not only that, you look at the plane curve. So there, X is a plane curve. So in that case, your EHK of R is 3D mod 4 plus L square upon 4D P2S. So what are these numbers? So L is some bounded number. And now your Suzuki bundle is of rank 2. S is the number where F to the S minus 1 Frobenius is semi-stable and F upper star S is not semi-stable. So this number S tells you, dictates which stage of Frobenius the bundle will start failing to be semi-stable. And L is how much it has been destabilized. That's the measure. So okay, so this is kind of characterization. So you look at the plane curve and come back to the example of Monsley. So this, if you combine that one with this one, so it just says for these kind of prime, your Suzuki bundle is not going to be semi-stable, it's not semi-stable. And for these primes, the Suzuki bundle is semi-stable. So in particular, the strong semi-stability is not an open condition. That's what it gave an example. Okay. Any questions so far? we look at this, we introduce a new invariant now for a graded situation. So most of the examples that when it comes for the computational purpose, they tend to be all graded thing because they were applying various techniques from geometry or Grobner basis kind of combinatorial thing. So here we actually stick to only graded case. So R is a standard graded ring. Let X to be Raj R. R0 be algebraically closed characteristic of K to be P positive, and I again to be an ideal, graded ideal. Such that length of R mod I is finite. Okay. So given R, you have fixed R, you have fixed I again. Now I define a function instead of a number as follows. So first you define Fn, a function from positive real line to this as follows. Fn of x defined to be 1 upon, so d is the dimension of your ring now. So d minus 1 is dimension of x. So d minus 1, then for R mod IQ, m, if m is equal, if x equal to m mod q. So remember your q is Pn. So q is Pn. Now it's better to explain the picture now. So what I do, 0, you have 1 over q, 2 over q, like that. 3 over q, define. So 1 over q, you know one number because x is 1 over q, so 1. Then 2 over q, you'll know some number. Like that, it will go on. Join them. This is going to be your Fn. So for each 1 over q, 2 over q, 3, I define the map, like it is graded m, for m over q, the mth piece of the graded ring. The R mod IQ is a graded ring, again, because I is graded. These are graded rings, the mth piece of that you define if it happens to be unknown. So this is, or other way I can look at is this is 1 over q, 2 over q, 3 over q, like that. Now, so I define a step function, 0 as function. So this function is called Gn. So at each n or q, you associate a function, Fn or Gn, that you have. So now, the theorem is this now. So it says if dimension of R is greater than or equal to 2, then Fn n belonging to n is a sequence of compactly supported piecewise linear continuous function. Okay. So what? Such that Fn, I look at the sequence Fn or Gn, they are uniformly convergent. So they are uniformly convergent to what mm. So you can say it's an L infinity norm also. But here, let me say fx to be the limit of this fnx, which is same as limit of gnx, and tends to infinity. So given each q, you have defined a function fn, and now you have defined a function. Earlier you have defined a number which was a length, now you define a function. And for each x, you look at the limit. So that limit exists, that's the assertion here. And call that function to be fx. Then ehk of this pair, r of I, is integral of this function. So what is the point to be noted here? That we give some application now, but before that there are some things hidden here which I have not said. As one, the union of support of these functions fn, in fact, itself is contain a compact. So that ensures your f is compactly supported. Okay. And second, fn converges to f uniformly in several ways. So this one has not made it clear. So, okay. So definition. So you had a pair Ri, and you define a sequence of functions and took its their limit, and that limit you call it to be Hk density function. So this you call, which is from 0 infinity to R, called Hk density function, and instead of writing in such a long way, I'll denote it by f mod. Okay. So you have given a notion of Hk density function for a pair Ri, and for a pair Ri, you had a notion of EHK also. So EHK already we know in curve case. So what is HKD? So that's the thing. Let X be a smooth curve. Corresponding section ring is Rm. So as before, it comes with a Syzygy bundle. OX to OX1, 0. And let strong Hn data of V be given by these numbers: AI, Ri, ranks, slopes, ranks, and the degree of the curve. Okay. In that case, what is the Hk density function? So I will draw it. So you have a 0 here. Then you have 0.1 minus A1 upon D. I should write it up. You have this. The second is 1 minus A2 upon D. Then go on. 1 minus AL upon D. And the last is 1 minus AL plus 1 upon D. So these slopes were decreasing, so they are increasing here. So you took the minus thing. So the thing is, I missed out one here. It's the one I'm supposed to be. So there's one here. So there's one, and increases. So, and these are really point of similarity. There is no smoothness. So if you look at this diagram, it suggests that your HK density function exactly similarity at those slopes. So there is a one-to-one correspondence between this data and the HK density function of R. So this function completely recovers the data as strong as in data for the Trivedi bundle. Okay. On the other hand, so in practice, when you are computing EHK versus HKD function, so what happens in the graded case? You are looking at, to compute EHK, you are looking at the qth place and computing all the length of all degrees and then adding them up and then taking the limit. In the HKD, when you're looking at the mth place which corresponds to x, you're computing the length of that and you're taking the limit. So the work is more or less same in practice. So, but it covers more data. That's one thing. It is a multiplicative function, so this I will say. So in what way it is multiplicative? So you x and I can take the ring also, that x and k2 projective varieties with HKD function. So I have to specify my ideal also, but take maximum ideal, for example, HKD functions. Fx and gx respectively. Then your x, the key function of the Segre product. So I'll Segre product, okay, I'll do that. Of x and y is what? Degree of x into x of d1. So dimension of x is d1, dimension of y is d1, d2. So they're all greater equal to 1. So this is bad notation. So x to the power d, d1 factorial g of x plus degree of y, x to the power d2 d2 factorial into f of x. So this is a polynomial in x minus the function fx into gx. So this is kind of a multiplicative property holds here. Segre product. You one way you want to look at ring way. So you take x, associate so r direct sum of Rn, y given by direct sum of Sn. So you can define the Segre product Sn as to be direct sum of diagonals. So these are over same field, it should be, of course, both of them. So over K, the tensor should make sense and return equal to 0. And now you take the proj of this ring. So that's the Segre product. There. So what it tells, so in particular EHK of the Segre product, I can just take the integral of this. Okay. So at once it tells me that HKD of Segre product of, say, you take n curves or S curves, non-singular curves is a piecewise polynomial of degree S with rational coefficients, polynomial rational coefficient in QX. So I said piecewise, so they'll have singularity also, and the singularities are rational points. So okay, so this is because if I take a non-singular projective curve and take its HK density function, it's a piecewise linear polynomial. So I put it this result, so it just says piecewise degree S polynomial, and singularities are rational point. So at one, so EHK of such a Segre product is just an integral of this function. So this is belongs to a rational number. So that you get it for free that it is a rational number. That's okay. And this, so without much competition you get that. And then other thing it tells you, you can express EHK of Segre product in terms of strong Hn data of their syzygy bundle. Okay, but it also, when you really look at two curves and two rational, their syzygy bundle, it immediately tells you EHK is not a multiplicative function, in fact, because the answer will come, suppose V is a semi-stable bundle for the X, it has a strong data like AI, RI, something like that, and Vy has a Hn data of Bj, Rj. So this function EHK will be expressible in this form, but it depends very much on their relative position of AI's, Bj's on the real axis. So they are kind of intermixed terms. So the EHK is not a multiplicative function. So what about a tensor product? So, but if I look at the tensor product of two rings, to compute EHK of those rings is fairly easy. In fact, EHK of tensor product of R tensor J with respect to any ideal J, tensor J is EHK of R into EHK of S. So this is nothing to do with HK density function. This you can compute, but look at the HK density function of this one. This is rather complicated. So HK density function of, say, R tensor X. Okay, forget. Let's assume it's maximum ideal. Is, suppose I call it H. So H of X is going to be 0 to X. So HK density function of R df and HK density function of S dg. Suppose this is given to you, then HK density function of the tensor product is f of y into g of x minus y dy. So it's a convolution function. So this suggests something. So we'll come back to this later, in fact very soon. So there's more application of how this HK density function behaves when you take power of ideals, but it gets technical. Now I would like to say what happens in characteristic 0. This is a concept defined for characteristic P. So the way to approach would have been, of course, that you have a ring R, I, or take R to be a Z algebra over a field of characteristic zeros. So K finitely generated K algebra. Think of some geometric ring, finitely generated K algebra. So here, sorry, this is maybe, let's not make a heavy weather out of this. So it's a standard graded ring. But question, of course, you can ask in any setup, it's a graded ring over K, where K is of characteristic 0. So can you define the natural way, and I is of course ideal. So the way generally has been dealt is that you take a spread of Ri. So basically, so you make choose a Z algebra A, finitely generated A algebra. Finitely generated, so A is a finitely generated Z algebra, so that your R, this thing is definable, ideals and all. Ra, call it IA. So this is a family defined over A. So now for almost on almost all P or on the open set of A, spec A, you look at the fiber, so that will be over some prime ideal, prime number. So call that reduction mod P, or I think I won't make it very precise. So this is reduction mod P of the pair Ri. So you have a thing in characteristic 0, you manage to go to characteristic P, taking reduction mod P. Now for almost, so you now for P, of course this compute EHK of this pair, now it is in characteristic P. So you define P limit P tends to infinity, which is EHK, people call it infinity of R. But question is, so this is the most natural way to define. Just go reduction mod P and define the limit. But what does it involve, this limit? So this, so you beware it. I mean, I'm not saying it exists, but so strictly speaking, it involves two limits. So this is your P tends to infinity, and you are taking limit n tends to infinity, 1 upon QB, length of R mod I to the power Q. You have to deal with limits at once. So this is a problem. So when, again the answer when curve is non-singular, so this is an old result actually. So EHK, if dimension of R, if X is a non-singular projective curve. Sticks here that the EHK exists. Here I would say when this theory of HK, this EHK multiplicity came out, example of Monsky was, so vector bundle people were actually surprised to see that there are actually, you can find that it's not an open condition. I thought that semi-stability. So it basically it used vector bundle but gave back something to the vector bundle theory. Here, actually we make, again to prove this theorem, we go back to vector bundles. And there we had to look at the result of Shepard-Barron. We use it to crucially say that as you take a Hitchin filtration characteristic 0 and go mod reduction P, you will have more and more filtration, but for large enough P, they seem to stabilize. They become, so, and not only that, the slope of the other ones you can compute into slope of, compare with the slope defined characteristic 0. So the answer EHK infinity Ri, which you get ultimately, which involves the slope of the vector bundle. So Hn of the vector bundle. So I'll just expression or polynomial in terms of slopes and ranks of Hn filtration of V, which is defined characteristic 0. So that way it has a nice interpretation. But for higher dimension, one doesn't know. The only only thing one could come close to it is you can try to make it this limit easier. So this t tends to infinity. I'll just write it 1 upon q to the t to the power d minus 1 d. So you don't have to take all the Frobenius Kullbacks. You take the d minus 1 Frobenius, which is the dimension of your x, and compute there. So this was when d was 2, it was proved by Brenner. Means existence of limit I have put, but this is sufficient, is proved by them, Claudia Miller and Lee. Okay. So they ask a question whether it's true for higher dimensions. So actually the answer is correct. And here you use the theory of HK density function. I said in a cryptic fashion that H converges to several ways uniformly. And that's what you're using to permute the limits many times. So that's one application. So for D greater than 2, this is also correct. Okay. So after that, now I'll give the last line of my talk because I said I'll introduce some complex numbers. So we saw that when we take tensor product of rings, the xk function becomes a convolution function. So this is something, and it tells you like now you have f, which is a continuous function. Real valued continuous function with compact support. So look at its Fourier transform. So, which will make sense now. This is in fact L infinity function, the f. So this makes sense, Fourier transform. So when you look at Fourier transform, the first thing is that you have this function and you evaluate it at 0, this is going to be your EHK. So EHK is just a point of a Fourier transform. That's one thing. Now if you, and so this one is, that convolution thing, it just says the Fourier transform of tensor product is just a product of the Fourier transform, so that was nothing. Great, so here I again go to the curve. Non-singular curve. So what is the Fourier transform? So you had f hat t will be given by some constant, which is, I forgot actually, this is some depending on the ring, I to the power t. So that's what I commented, I'll use some complex number. Okay, then the rank of your OX1, which is 1 actually, into, but I choose to write it this way, I into t of mu of your OX1, which is d upon d, which is 1. So this is nothing great, I'm saying. Then minus rank of the middle bundle. So you had this. OX1 to 0. Rank of IT, mu of the, this is 0 of course, but this kind of looks alternating sum. Rank of e to the power. Rank of this direct sum of OX. And the next one is plus summation Ri is the ranks of those strong Hn data, into e to the power minus I into Ai of V upon D. So this is alternating sum of the slopes, e to exponential to the power something. So what's the meaning of this? We don't know. So each individual, if I look, this is not holomorphic function, but when these are added up, this is a holomorphic function in fact. So that's it. Maybe some harmonic people can